Well, now we want to talk about something called the common ion effect. This is very important. If we look at the equation, we will notice that there on each side there's something that's common. We've got an ion over here, and the acid also has that same species. So it is common to both the acid and what we call the conjugate base. So a common ion, another way of looking at it, would be to say that the formate ion is common to both the acid and a salt. So you can see that formate is common to both the acid and the salt. So if we were to add the salt, and you know that in this case sodium compounds are always soluble, if we were to add that, it's essentially like adding that species on the right, and that's going to shift the equilibrium. So let's take a look at how that works. What would be the effect on the equilibrium if the salt sodium formate were added? Would the equilibrium be shifted to the left or the right? Well, let's look. If we add a species on the left, according to Le Chatelier's principle, that's going to push the equilibrium to the right in order to use that up and reestablish the equilibrium. So what would happen to the concentration of hydronium in that case after the salt with the common ion is added? What would happen to our acid? Would that go up or down? What would happen to the pH? These are very important questions. And I'm going to go ahead and do the calculation, and then you can come back and fill that in. So, the common ion effect. What is the common ion between the salt, sodium formate, and formic acid? It's the ion formate. So if we were to mix 3 milliliters of 0.1 molar sodium formate and 3.0 milliliters of 0.10 formic acid, what would happen? When I measured the pH, it was 3.90. That pH is higher. What does that mean? So the pH went up from just having the acid by itself. So that means that the equilibrium shifted to the left. The pH goes up, it's because the hydronium decreased. And that's what Le Chatelier's principle would predict. So 10 to the minus 3.90 is 1.3 times 10 to the minus 4th molar for our hydronium. All right, let's do the concentration of the acid after dilution. And by the way, after dilution is going to be, or after mixing, is going to be the value that we use at the beginning, the initial, before equilibrium is reached. Okay, it doesn't matter if we use milliliters or liters, they'll cancel. So we could use either as long as they're the same. So our concentration of our acid is 0.050 molar. Again, let's review. We've got 2 sig figs. It's after the decimal place. We've got 2 sig figs here, and we've got 2 sig figs there. So we're being consistent. The common ion, the sodium contained in the sodium formate, is going to be the same. But I'll go ahead and complete the calculation. Again, as long as those units are the same, we can cancel. All right, so again, for the third time, let's calculate the Ka under these new conditions where we've added the common ion. All right, in the case of the common ion, previously you'll notice that the common ion was 0. In both cases, it was 0. This time it's not 0. So what we have now calculated for the acid and the salt, those are our initial concentrations. Now what about hydronium? The hydronium is going to be 0 for mathematical purposes. Now is it ever 0? No. But for mathematical purposes, so that we can solve this, we're going to say it's 0. Equilibrium is reached so quickly. It's one of the fastest chemical reactions, the transfer of a proton. Okay, so this is going to go up 1.3 times 10 to the minus 4th. Now wait a minute. Maybe you're wondering, how did I know, because these are equal, how did I know which side was going to go up and which side was going to go down? Well, we can't go down from 0. We can only go up. So that's how we know. Again, the same equilibrium expression. We're just in the habit of doing it over and over again, and that's a good habit to be in. Make sure whenever you take a quiz or exam, you write out the equation and the expression, which is what I'm doing here. Okay, so let's go ahead and calculate the value of Ka. I'm going to go ahead and do that addition and round to 2 digits at the end. It's going to turn out to not make a difference, but sometimes it does. Okay, and our Ka turns out to be 1.3 times 10 to the minus 4th. And a note to self, it's the exact same as the hydronium in this case, and there's a reason for that. So let's calculate the average Ka from these 3 experiments, because it's a constant, so it should be the same. So let's take a look. We had, in the first case, 4.5 times 10 to the minus 5th. And then the second time it was 4.6 times 10 to the minus 5th. And then this time it was a little higher at 1.3 times 10 to the minus 4th. We're going to add those together and divide by 3. And we get an average of 7.4 times 10 to the minus 5th. So that's our average experimental Ka. Okay, and if you look at the accepted value, it's 1.8 times 10 to the minus 4th, and that's out of our textbook. So let's calculate our error. And then I want to talk about the magnitude of the error. over the accepted value times 100, and we get a percent error of 59%. And some of you would think, whew, that's terribly high, especially after titrations where we want you to be under 1% error. How come we have 59%? Is that terrible? Well, the answer is, when we're measuring equilibrium constants, it's quite common to have an error that's rather high. 59 is not a terrible error considering those pH pens. You think about those pH pens measuring something that is 1.3 times 10 to the minus fourth molar. So you're measuring these tiny, tiny hydrogen ions, and there's very, very few of them. It's quite remarkable that we even get this close. Those are quite remarkable little devices when you think about it. So their accuracy is not as good as if, let's say, other types of instruments. So measuring equilibrium constants, those are very difficult to measure very accurately. So 59% using that equipment is not at all too bad.